Hi, welcome to my video. This video, let us see some of the criteria for subspace. Already in my previous video, I have done one criteria and this is going to be the second one. The necessary and sufficient condition for a non-empty subset W of a vector space V of F to be a subspace of V is A, B in F, and alpha beta belongs to W implies A alpha plus B beta belongs to W. That means the theorem says that if you assume W is going to be the vector subspace for V of F, then the equation A, B in F, alpha beta in W implies A alpha plus B beta belongs to W must be true. And similarly vice versa. If this equation is true, then W must be the subspace of V. So let us assume the necessary part and prove the sufficient part. So the necessary condition is that W be the subspace of V. Let us assume W is going to be the subspace of V. Then according to the definition, W is closed under vector addition and scalar multiplication. Hence, for any A in F, alpha in W, since the scalar multiplication is closed and it is also W, you are assuming that it is a subspace of V, then obviously A alpha must be in W. The same way for B in F, beta belongs to W, B beta is also in W. So let us add A alpha in W, B beta in W implies A alpha plus B beta belongs to W. So this is possible because W is going to be the subspace of B. So it's closed under vector addition, hence the proof. So for any A, B in F, alpha beta in W, that implies A alpha plus B beta is also in W. Now let us see the sufficient condition. So let us assume the converse part, it goes as such. Let W is going to be a non-empty subset of V satisfying the conditions A alpha plus B beta is in W. That implies for any A, B in F, alpha beta in W, A alpha plus B beta belongs to W. Now what we have to prove is that W must be a subspace of V. So to show that W must be a subspace of B, let us take some substitutions and then we can prove from that. So the first substitution goes as such. Let us take A is 1 and B is 1. Then substitute in that equation 1, we get for alpha beta in W, alpha plus beta is also in W. So that implies W is closed under vector addition. And then the second substitution goes as such. Let us take A is equal to minus 1 and B is equal to 0. Again we are substituting the same equation. We arrive that minus alpha belongs to W. That means for any alpha in W, minus alpha is in alpha W, that is the additive inverse of each element of W is also in W. So each element of W has an additive inverse and that is also in W. Then the next one is going to be let us take A is equal to 0 and B is equal to 0 in equation 1. Then we have that 0 into alpha plus 0 into beta belongs to W implies 0 is in W. So that is the 0 vector also belongs to W. It is also in V, it is also in W. As the elements of W are also the elements of V, vector addition is associative as well as commutative in W. Hence, W is an abelian group with respect to vector addition. Now, the last substitution is going to be, let us take that beta is equal to 0 in equation 1. We get A alpha plus B into 0 belongs to W. That implies A alpha is in W. So, W is closed under scalar multiplication as A is in F. So, the remaining postulates of a vector space is also hold good in W since they hold in V of which W is a subset. Hence, W of F is a subspace of E of F. So, both way it is going to be true. So, W of F is a subspace of E of F means that we can easily prove by taking alpha beta in W and AB in F and just substitute A alpha plus B beta belongs to W. We check that and if it is belongs to W, then we can say that according to this criteria, W of F is a subspace of E of F. Thanks for watching. See you in the next video.